Hi everyone, welcome to the Mechanics and Materials 1 channel. This is Burak Görmüş, and in this video I will be explaining the MATLAB GUI that can be used to solve beam bending problems. When you open the app, you can see the homepage as shown here. In this GUI, there are 5 tabs. The first one is the homepage. The second one is the manual tab, where you can create your own beam geometries and analyze them. The next one is the book solutions tab. In this tab, you can choose a problem from the textbooks of Hibbeler or Beer. When you choose a problem using this tab, the geometry and the boundary conditions will be already assigned. The next one is the material properties tab, where you can see the characteristics of commonly used materials. And the last tab is the references. Let's start with the manual tab, in which you can create beam structures and assign boundary conditions. In PostProcess, you will be able to create the beam geometries. The first step is to create the nodes. In this app, it's assumed that the beam will be located on the x-axis. Hence, the only thing you need to do is to assign the x-coordinates of the beam geometry. As you can see, as you push the Generate Node button, the nodes shown in the figure at the right are generated. The second step is to create the elements. While creating elements, you need to specify the nodes of a particular element. For example, we can connect node 1 and node 2 and create our first element. We can also connect node 2 and node 3 and create our second element. As you may observe, as we create the elements or nodes, we can see how many of them are created here. One extra feature that can be found is to turn off and on the node labels by using this switch. We can do the same thing for element labels too. We can also play with the size of the nodes and elements in order to change the view. When you want to get an information about the coordinates of nodes, we can say show nodes, and for example, the first row has 2 columns. Since it is the first row, it's our first node, and the first column is the x-axis, and the second column is the y-axis of the first node. We can also say show elements, and we can figure out the nodes at the edge of an element. Exemplifying, the first element is between node 1 and node 2. The next feature is that we can import a beam geometry from an Excel file. Lastly, we can push the Remove All button and clear the geometry that we just created. In the Process section, you can assign the boundary conditions. Firstly, we need to enter the number node and magnitude. For example, let's say we have a fixed end at node 1. For a fixed end, we know that the displacement and the slope are 0. If we want to assign a boundary condition related to displacement and slope, we should select Deflection below Boundary Condition type. Now, I am entering the boundary condition information that the displacement is equal to 0, and I need to push the Apply button. After that, you will see a triangular shape below the node indicating that the displacement is equal to 0. Subsequently, I'm choosing slope for node 1 and assigning this boundary condition information. As a result, as you can see, a dashed line appears. Let's assume there is a roller at node 2, meaning that the displacement is equal to 0. And now, as you can see, I am assigning this boundary condition. Lastly, assuming we apply a vertical shear force at node 3, having a magnitude of minus 10 kN, I am entering the node number and the magnitude. After that, I choose Load from Boundary Condition type and push the Apply button. If you enter a boundary condition that is different than the boundary conditions already assigned, we get a message from the GUI. So let's try it. If I enter a shear force having a magnitude of minus 5 kN at node 3 and push the Apply button, I will be asked whether I want to change this boundary condition. If I click yes, the boundary condition is updated. If we want to assign a bending moment, we should also note that load should be chosen under boundary condition type. In the process section, we can also assign a distributed load. Assuming there is a distributed load having a minus 5 kN of magnitude between node 1 and node 2, I am entering the information needed below the distributed load box and push the Assign the Distributed Load button. If the boundary condition needed to be cleared, we can push the Clear Boundary Conditions button and remove all the boundary condition that has entered. In the post process, we need to push the Run button and analyze the structure. Before pushing the Run button, we should also change the Young's modulus and inertia if it is needed. After pushing the Run button, in the left bottom, you will see the elastic curve and the displacement values throughout the length. In the right bottom, you will see the displacement and slope values for the nodes in which we do not know this information already. Further, it is possible to see the reaction shear force and bending moment for the nodes in which you already assigned the displacement related boundary conditions. If you want to see the original shape of the beam before deflection, you can turn on the reference button. If you don't want to see the nodes on the elastic curve, you can turn off the Show Node switch. Playing with magnitudes will yield a magnified version of the elastic curve, and the original elastic curve will remain as a colorful surface plot. If you choose a button under Color Ball, it is possible to change the colors in the elastic curve. At the top of post-process, there are two buttons, Show Max Displacement and Show Equations. Pushing Show Max Displacement will show the maximum displacement value as well as the x-coordinate of this deflection. Pushing Show Equations will yield the cubic polynomial equations for each beam element. At the bottom of post-process, there is a Save Figures button, and when you push that button, the original geometry of the beam as well as the boundary conditions as appeared in the right tab and the displacement figure will be saved. Pushing Reset Views clear the displacement figure, and if we want to analyze a new beam structure, we can click Clear Everything and start the procedure again. Lastly, let's look at the Book Solutions tab. In this tab, you can find some of the beam bending problems given on Hibbler 10th edition or Beer-Johnston 9th edition. Firstly, you need to choose a book. Then, you should select the problem number. After you select the problem, you can see that the geometry and the boundary conditions are already assigned. Further, the Young's modulus and inertia values are already assigned if they are given in the problem. Let's look at the problem 38 given in chapter 12 of Hibbler. As you can see at A, we have a pin. So in the GUI, you can see that at node 1, we have a zero displacement shown by blue rectangle. At node 2 and 3, we have a transverse loadings having a magnitude of 30 and 15 kN. Lastly, at node 4, corresponding to B in the problem, the displacement is 0. Now, all you need to do is to click the Run button and analyze the beam. After that, in the post process, you can see the results. Let's also try a problem from Beer-Johnston. After you select the problem again, all the previous work is removed and the geometry and boundary conditions are assigned again. Clicking the Run button again, we can examine the problem and see the results.